There we are. Everyone hear me all right on Zoom? Is this appropriate? Appropriate volume and everything? There's no dissent. I'm just going to keep going. Cool. Well, hello, everybody. My name's Jordan Mugglin. I'm a senior mechanical engineering student at Bethel University. In the previous summer, I got to work in the fluids lab at Bethel under Dr. Stein, who's in the back of the room. And my specific project, we were trying to look at vortex shedding and other periodic flow functions, specifically for use in educational and laboratory purposes. So, oh, hello, there it goes. So the project here and the subset of my funding and the goal was actually to develop a lab for use with our fluids mechanics course. We have a significant single fluids course in the physics curriculum at Bethel, and that includes a lengthy lab component. So I'm just here helping out, trying to create a new exercise for that. Specifically, what we are trying to do is image low speed flows, relatively laminar flows, which means straight-ish fluid, and observe phenomena that might be occurring in there. A little bit about how I'm going to structure this talk. I treated this as a design problem. I'm an engineering student. And so what I'm going to do is I'm going to give a little bit of an overview of the physical processes behind what's going on here. So it might feel a little bit like a review of general physics for a little bit. Sorry. And then I'm going to talk through my design process. So here we go. An important aspect of this as well that we wanted to implement was there's a physical element to this project, actually developing a rig that'll do what we want to do and looking at it, and also creating a numerical model using simulation software such as COMSOL, which is what we use in this case, because this is a significant tool in the realm of fluid dynamics and fluids research, because by creating a digital model, we can match that to reality and then learn a little bit more about things that we might not actually be able to see. Because if you think about it, we really can't, like, it's hard to imagine how the air is flowing in this room. We can't see that. So we need some techniques to figure out what's going on if we want to study it in a practical perspective. And that's what this numerical element helps us do. Another thing here, we've got three kind of significant chunks of physics that I'm going to go over. Flow visualization. So we use optical techniques. Bethel has a long history of excellence in optics programs. So that has a big role in this project. Some basic fluid dynamics and some heat transfer. This is how we chose to drive things, which plays into our visualization techniques. All right, this is the flow that we're interested in studying, periodic motion or vortex shedding more accurately. What this is when you've got fluid flowing over an object, there's eddies that form behind that object if you've got a relatively laminar flow. It's all governed by this equation here on the bottom, which is cut off by the bar, but it's F equals S times U, which is the fluid velocity, over D, which is the diameter of the cylinder. As we get variations in pressure differences behind the object, we see this periodic eddies coming in behind. If you like took a stick and swung it through the air and heard a whooshing sound, it's kind of a similar phenomenon. And everything's governed by this equation here. It's simple. Frequency equals velocity over diameter times something called the Struhl number, which is a dimensionless number that's common in fluids. It changes with respect to another dimensionless number called the Reynolds number, but generally the Struhl number is about 0.2, which is significant in how we were telling you if we were actually able to detect this phenomenon or not. Just a little bit more about vortex shedding. Oh, there it goes. It happens on all scales. So if you look at this picture here on the left, you've got a laboratory setting recreation of this, and here on the right, you've got clouds forming these vortexes in the wake of an island. So this is a phenomenon that occurs on all scales and really creates some striking images sometimes. Next, I want to talk a little bit about the optical techniques that we use to actually view this motion in air, because air is transparent. And the first one is Schlieren imaging. So Schlieren imaging is a technique where you take a light source, we use a red LED in this case, shine it on a mirror, and then back across a knife edge that's placed at the focus of the mirror. Now, and then that goes to a camera, or sometimes we use a pane of frosted glass. This here is a camera. You're seeing the image of my little cloud of sulfur hexafluoride. But by having gas or other fluid in view of the light from the Schlieren imaging, kind of in this test area in front of the mirror, you can visualize density distortions. So hot air causes a change in the density of air, which changes the index of refraction and causes the light to just behave ever so slightly differently. And by putting the knife edge at the back, at the focus, we can cut off some of the light that's been refracted differently and actually image what's going on. So here in this picture, you see a little cloud of sulfur hexafluoride that I was flowing over a piece of, I think that was acrylic I was using, and he pops up here. A very cool way. That is a really laggy mouse. I'm not going to use that as a pointer anymore. And allows us to image stuff like that. Second optical technique we used was called Mach-Zehnder interferometry. This is a technique that also utilizes kind of variable density in order to image things. But in this case, rather than having it kind of all be in line and dealing with focus and a knife edge, we have a laser beam that we separate into two paths. We collimate one of the paths, so we make it so that the one laser beam expands out into a bigger circle, and it can cover a wider area. And we shine that across the sample area that we're interested in studying, where the flow is going to be happening. After it shines through that, we recombine it with the other arm, and then by looking at the interference pattern, we can make determinations about what's going on, and it's a little bit more quantitative than Schlieren imaging is. This is a picture of what the interference pattern looks like. That's about a two inch by it's about a 2-inch diameter circle that we were able to study. There's a little bit about interference that I'm going to skip over, but basically we've got constructive interference and destructive interference causing these light and dark fringes. Now, as we have the variable density, it actually allows us to move these fringes. So here we have a candle placed in the apparatus. As you can see, the lines are all distorted, and by counting how far those lines have moved, we can actually infer backwards to make determinations about what's the density field, and then therefore the temperature of what's going on in the actual flow region that we're interested in studying. So it's just a little bit more quantitative than Schlieren imaging, but it's harder to view a big area. It's the trade-off. This is kind of what I was working on designing. So this is kind of a first early stage, first pass. Let's see what's going to happen. Prototype of my flow generation rig. We just have a simple 3D printed cylinder suspended over a hot plate. That one was originally intended for heating coffee. That flows up through a flow straightener, which is essentially a whole bunch of straws that were glued together that Dr. Stein had lying around. And we just wanted to see if we could generate this simple flow by having an isolated cylinder. Here's some kind of early results. So as you can see, we have some swirl going on in the Schlieren image on the left, but it's not quite in the center of what we're looking for. And here we have what the flow kind of looked like in the moment in this GIF here. Basically, with this model, what we started seeing was, the slide back there it goes. We started seeing artifacts of the flow we were looking for, but it wasn't quite as detailed as we would have liked, and as we would have to study. So we continued on to use computational fluid dynamics and simulation software to actually improve our design. So a word about this. It's just a numerical experiment, like I was mentioning before. It allows us to explore physical process that we then used, and I will skip over this briefly, to improve the design. So this is essentially a simulation I created of that first prototype. We've got open boundaries on the top and sides, and we've got a hot plate down at the bottom that's cut off by the bar that's driving hot air, in this case, to rise up through the platform. Now, I had been expecting it to keep rising straight because there's no wind introduced into the system. But as we can see, we've got actually a drift going on in our periodic motion, which surprisingly was consistent with what we were seeing in reality. So with a mind to fix that issue, I set out with some redesign. So in this simulation that I'm pulling up now, if it goes, no, there it goes. No, okay. I put walls in on the sides. I had been worried about that initially, introducing too much friction and causing more distortions in the flow, but in the simulation, it produced a much clearer vortex pattern and a much more consistent flow that we then used in our second design iteration. So this is the second prototype. It has walls, it's got an acrylic base. On the bottom, we've got a piece of aluminum that I just machined a million holes into to replace the flow straightener and try to create as much of a straight up and down airflow as possible to create 2D flow. And here's some results of that. It kind of looks like the fires of hell a little bit, which I think is cool and also terrifying at the same time. Here we see more kind of fluid artifacts and swirls, but it's kind of wild in this stage to the point where we kind of can't make out flow that we're interested in seeing and studying. So this led to design iteration 3, which was the one that actually kind of started giving us results. In this prototype, we took the base and we, on the inside of the mount, we put in like a fillet. So it's rounded to try to drive flow only up this way into the shaft to create a 2-dimensional flow pattern, because once you start getting into 3 dimensions, we start getting extra noise like we were seeing on the previous slide. And this is the one that kind of worked. It generated a 2-dimensional flow, and I had options to put in wood blocks to kind of change the width of the system. And this gave us results that, using an iPhone's slow motion video and some basic software on my computer, I was able to calculate a Struel number down to 0.3. That's not exactly what we're looking for, but it's in the ballpark, and it means that we're on the right track with something here. So here's some pictures of what that looked like. As we can see, we have a much clearer swirl here. I'll play this little video quick just to give a brief taste of what some of the stuff I was looking at looked like. And by extrapolating it, if it goes, which it may not, because I'm running Zoom at the same time. Seconds. There it goes. On my computer, at least. There it is. By going in and tracing some of these little individual details and following that up with a scale on the side, we're able to work backwards, figure out a Struel number, and determine that we're actually starting to see some periodic motion within this system. Okay, go to the next slide. There we go. So just review once it goes to the next slide. There it goes. Just a little bit of an overview of the work of the summer then. I was able to simulate and observe periodic convective flow in a physical system, design and redesign an apparatus, as well as learning how to use a whole bunch of fun toys in a machine shop. Analyzed the flow, found Struel numbers. We're on the right track for further redesign as that comes down, and I had a good time doing it. And that is what I got. Any questions? Good? Anybody?
Can you explain to me what a Struel number is?
Yeah, so a Struel number is a dimensionless number that describes flow. It's it varies with another number called the Reynolds number, which is dictated by like the velocity of a flow that I wouldn't get into, but in this case, it's essentially a constant that just qualifies that equation when we're dealing with this particular type of flow.
Does the Struhl number change depending on like the atmosphere or?
I don't think so. Dr.
it's always
Stein,
just one
correct me
number.
if I'm wrong there, but I'm pretty sure it stays.
Well, so like you mentioned, it's slightly dependent on Reynolds number,
Yeah.
right? So, so in that sense, yes. But you also are correct that over a broad range of Reynolds numbers, it's fairly constant.
It applies to water, air, general fluids as well. So,
Thank you.
This is to be used in the future in a class.
that's the idea. It's not finished in its current state. There's more design that needs to be done, as well as refining of the actual analysis process and writing a lab. But that was the goal of the project and is hopefully going to be implemented after some more work on it.
All right, any last questions? Okay, let's go ahead and thank our speaker.
Okay, so remember, this is the end of this session. Next up is another exhibit session. We will show the exhibit promos. If you want to stay for that, you don't have to. And fill out your ballots. Why don't you leave those with me before you leave the room? Your recording, you want to turn off the recording and then restart it with the promo video? Well, you want to run the